Good morning, students. Today we are going to discuss about the Maxwell's equations in integral forms. So the four Maxwell's equations are del dot D is equal to rho is the first Maxwell equation, and del dot B is equal to 0 is the second Maxwell equation. Third one, del cross E is equal to minus dou B by dou T, and del cross H is equal to J plus dou D by dou T. These are the four Maxwell's equations. In today's class, we will derive what are the integral forms of these Maxwell's equations and their physical significance. Using Gauss theorem and Stokes theorem, we are converting these four Maxwell's equations into integral forms. Gauss theorem will convert the surface integral into volume integral or vice versa. That is, it converts the volume integral into surface integral or surface integral into volume integral. Stokes theorem will convert the surface integral into line integral or vice versa. That is, line integral into surface integral. Using Gauss theorem, we will convert the surface integral into volume or volume into surface integral. Using Stokes theorem, we will convert the surface integral into line integral or line integral into surface integral. So these are the two basic theorems which are used to convert these basic Maxwell's equations which are in differential form to integral form. Let us consider the first Maxwell equation, that is del dot D is equal to rho. Let us integrate this above equation over any arbitrary volume V. Then integral V del dot D into dV is equal to integral over V rho dot Vv dV, where rho is the charge density, that is charge per unit volume multiplied by unit volume. That is, this total quantity charge per unit volume multiplied by volume gives rise to the net charge enclosed in that volume. So this quantity is nothing but the net charge inside the arbitrary volume. On the left hand side, we have the volume integral. So let us convert this volume integral into surface integral using the Gauss theorem. So according to Gauss divergence theorem, this volume integral will be converted into surface integral as, so this divergence will go out, that is surface integral of d dot ds is equal to volume integral of rho dot dv. So this is the first Maxwell's equation integral form. Del dot D is equal to rho is the differential form of Maxwell's equation or the first Maxwell equation. Surface integral of D dot ds is equal to rho dv. Volume integral over rho dv is called the integral form of the first Maxwell equation. So we will define that d dot ds. So we call it as b dot ds, we will call it as a flux of the magnetic induction. So it is also d dot ds. This is the flux of what is d? D is the magnetic displacement vector. Electric displacement vector, and B is the magnetic induction. So we will call it as a magnetic flux here. Since this D is the electric displacement current, so this term is called the flux of the electric displacement current. So we will define this integral form of the first Maxwell equation as the net outward flux the net outward flux of electric displacement current. So this surface integral of some term multiplied by ds is the flux. So the net outward flux over a closed surface of electric displacement current is equivalent to the net charge enclosed within that volume. So this is the physical significance of the first Maxwell equation. I am again repeating, the net outward flux of electric displacement current is equivalent to the net charge enclosed in a volume V. So this is the first integral form of the first Maxwell's equation. Next, the second Maxwell equation is del dot B is equal to 0. So let us integrate the second Maxwell equation over any arbitrary volume V. So then the volume integral of del dot B is equal to 0. Simple one. First we will integrate the Maxwell equation, then by using the Gauss divergence theorem, let us convert this volume integral into surface integral. Then the surface integral of B dot ds is equal to 0. This is the integral form of the second Maxwell equation. Then what is the physical significance? The same thing. So this is also dot ds, that is the net outward flux of the magnetic induction over any closed surface is equivalent to 0. The net outward flux of the magnetic induction over a closed surface S is equal to 0. This is the second Maxwell's equation integral form. Next, third one. What is the third Maxwell equation? Del cross E is equal to minus dou B by dou T. So here remember that for the first two equations we will integrate over volume. For the next two equations we will integrate over the surface. So consider the third Maxwell equation, that is del cross E is equal to minus dou B by dou T. Then integrate the above equation over the surface S. Then surface integral of del cross E into ds is equal to minus dou by dou T of surface integral of B dot ds. For the two equations we have applied the Gauss divergence theorem. In this we have on the left hand side we have the surface integral. So we will convert this surface integral into line integral using the Stokes theorem. So using the Stokes theorem, on the left hand side, this left hand side term, this curl goes out, that is the line integral of simply the electric field strength E dot dl is equal to minus dou by dou T of surface integral of B dot ds. This line integral of E dot dl is nothing but electromotive force. So this is the integral form of the third Maxwell's equation. Hence, we will define the third Maxwell equation in integral form as the electromotive force around a closed path. The electromotive force around a closed path is equivalent to the negative rate of change of magnetic flux linked with that surface. Here it is the path, here it is the surface. The electromotive force over any closed surface is equivalent to the negative rate of change of magnetic flux linked with the circuit. This is the physical significance of the third Maxwell's equation. Next, for the fourth equation, same. Here we will integrate the above equation within a surface S. Then this equation becomes surface integral del cross H into ds is equal to surface integral J plus dou d by dou t into ds. Same as usual for all the four Maxwell's equation. In order to convert into integrate form, we will take only the left hand side part, and according to Stokes theorem we will convert this surface integral into line integral, that is line integral of h dot dl is equal to surface integral of j plus dou d by dou t into ds. So closed integral of E dot dl is the electromotive force. Closed integral of H dot dl is called magnetomotive force. The surface integral of J dot ds is called conduction current. The current flowing per unit area, that is conduction current, and this is the D is called as displacement current. Surface integral of J dot ds is called the conduction current. The rate of change of displacement vector is called as the displacement current. So we will define the fourth Maxwell's equation in integral form as the magnetomotive force around any closed path is the sum of the conduction current and the displacement current over the closed surface S. The magnetomotive force around the closed path is equal to the sum of the conduction current and the displacement current over the closed surface S. So these are the four Maxwell's equations in integral form. Along with the integral form, we need to write down what are the physical significance of these four integral forms. These four integral forms are derived from the Gauss divergence theorem for the two Maxwell's equations, and using the Stokes theorem for the remaining two Maxwell's equations. We will apply this Gauss divergence theorem and Stokes theorem to the left hand side terms only. These are the four Maxwell's equations in integral form.